We just finished saying that the derivative of a product is not the same as the product of the two derivatives. If you want to take the derivative of two functions multiplied together, it's the first function times the derivative of the second plus the second function times the derivative of the first. So we have a similar problem for derivatives of quotients. If you want to take the derivative of two functions divided together, it's not just the quotient of the two derivatives. We have here, we call it the quotient rule. So if the two functions are u and v, so you want to take the derivative of u divided by v, this is v times the derivative of u minus u times the derivative of v all over v squared. So that v squared, that's the bottom function multiplied by itself with no derivatives involved at all. So my preference, what I've done since high school, and you're welcome to use, I've always thought of it as that if I want to take the derivative of a quotient, it's the derivative of the high function and the low function. So the derivative of high divided by low is low d high minus high d low all over low squared. So d, when I'm saying d, that's take the derivative of. So low d high minus high d low all over low squared. I find it fun to say, so I've always remembered it. You can use it. Some people remember v du minus u dv all over v squared. Either one is fine. Whatever is going to work for you would be fine. So we'll just do an example here. If I want to take the derivative with respect to x of this quotient, it's 2x cubed plus 5x divided by x squared plus 3. This is the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom function squared. So let's get so the bottom function x squared plus 3 times the derivative of the top, the derivative of 2x cubed plus 5x, that's 6x squared plus 5. So that was low d high minus high, so 2x cubed plus 5x times the derivative of the bottom function, derivative of x squared plus 3 is 2x. And then this is still going to be a big fraction all over this bottom function squared. And I hope you're thinking, look in the numerator, I have to distribute that subtraction. Very common error, which we talked about a little bit before, is if you were going to move on and simplify this expression, which is not always necessary, but if you were going to, make sure that you take that 2x and distribute it, and then distribute the subtraction. So our last new topic here for 3.3, higher order derivatives. So we have some practice now taking derivatives. So if I have a function y equals f of x, and I ask you to take the derivative, you could call the derivative dy dx, you could call it y prime, you could call it f prime of x. They'll mean the same thing. Take the derivative of that original function with respect to x. And the result is a new function, a function that gives the slope of the original function at any point, at any x value. So since the result is a function, we could take the derivative of that result. If I take the derivative of a derivative, it's just called the second derivative. So if I had a function f of x, and I asked you to take the derivative, the first derivative would be f prime of x. The second derivative, the derivative of the derivative, is f double prime of x, or the second derivative. The third derivative, we would say f triple prime of x, and you can see the notation is written out for you on your paper. So let's try an example from that paper. Okay, so this first example says, how I would read this, it says, take the fourth derivative of negative 5x to the 8th plus 2x to the 6th minus 9x cubed plus 32x minus 1. Let me get the pen up. Alright, so I have a little polynomial here, and I've been asked to take the fourth derivative. So just for convenience, I like to keep my functions labeled. So I'm going to say that this original polynomial here is equal to y. Now the way I'm going to find the fourth derivative of it is to take the first derivative, then take the derivative of that derivative, take the derivative of that derivative, and I'm going to have to do it 4 times to get the fourth derivative. So if I'm going to call that first polynomial y, then the first thing I have to do is take dy dx. So the 8's going to come to the front. I'm going to have negative 40 x to the 7th plus 12. The 6 times the 2 makes the 12. X to the 1 less is x to the 5th minus 27x squared plus 32. The second derivative, now I'm going to take the derivative of the function I have here, is called d squared y dx squared. That's the squared. So 7 times negative 40 is negative 280. X to the 6th plus 60 x to the 4th minus 54x. The third derivative is going to be the derivative of this function that I have here. So we would say d cubed y dx cubed. Oh, now you're going to watch me see how fast I can multiply 6 times 28. All right, I got it. So this is negative 1680. That's a 0. X to the 5th plus 240 x cubed minus 54. Now to get what I wanted, which is the fourth derivative of that original function, I guess I better go to the next slide. Okay, I decided to come up to the top here. So the fourth derivative of y is going to be the derivative of the third derivative. So that's going to make, I've still got a negative here, 5 times 1680, negative 8400. X to the 4th. 3 times 24, so plus 720 x squared, and then the derivative of 54 is 0, so I think this is our final answer. I would say the fourth derivative of that original function is negative 8400 x to the 4th plus 720 x squared.